squared, how a disk can have mr squared over 2, but a single point mass has a moment of inertia of mr squared. Now, how is that possible? Right. So if I just look at this about the origin, I go to some distance r, and I have some. Why is the moment of inertia for a mass m different for the center of mass for a disk? This is a really important concept, right? Why is the moment of inertia for a single particle different than the moment of inertia for an extended rigid body? Because if you were to look at that extended rigid body like a disk, the mass is located throughout, right? It isn't all located at a distance r away from the origin, right? So what you have to do is you have to add in a little bit of mass here, you have to add in a little bit of mass here, a little bit of mass here, and these all have different radii. So when you sum up all of those, you get a center of mass for a disk. You get a moment of inertia for a disk that's different than the moment of inertia for a particle. And it's simply because the mass is distributed in these objects, whereas here it's all located at a single point. And that's why you get these moments of inertia that are different for disks than for single bodies. So this is something that we covered a couple lectures ago, but if you want to look at what the moments of inertia are, on page 274 of your book, you see moments of inertia, for example, a hoop that's being rotated about a central axis, and it's mr squared. If you have a cylinder, look for another one is a solid sphere. A solid sphere is 2/5 mr squared. A spherical shell is 2/3 mr squared. This disk is mr squared over 2. So there are every object has a unique moment of inertia. Okay, so that's important to understand. All right, so let's move on today to rolling torque and angular momentum. Okay, so far what we have considered is that we have some sort of rigid body and that we're rotating something about that axis. So for example, this turning seat, what we're assuming is that there's a single axis of rotation and that everything is rotating about that axis of rotation. We're going to be now considering what the effect of rolling is. So it isn't just this. Now what we're saying is, okay, so in this particular, right now I'm rolling this about this fixed axis of rotation. But rolling is we actually take the bike and we start moving it along the ground. This, right now, the force of friction from the ground is causing this to rotate as I move it along. So now what we're going to consider is smooth rolling motion. And smooth rolling motion is basically, we don't have, it's where the object, for example, in this particular case, is, as I move this along, it's rolling along the ground. But we're not going to consider the situation in which right now this is translating, but the wheel is not rotating. Okay? So this is, for example, this situation, we're not going to consider this. what we're going to consider is that it's moving along in this path so that there isn't any kinetic friction, only static friction. All right, so in smooth rolling motion, what we can say is, suppose I have some circle. This is a nice little treatment in the book. But imagine that I have a wheel just rotating about its axis. So this is rotation. Now if I have something rotating about its axis, then the velocity v here is equal to the velocity v at the top. Now if I have translation, what is this going to look like? So I take this wheel, and now I just go like this. What would that look like? What would all the velocities be here? What would the velocity of the center of mass be? Just going to be v, right? How about the bottom? Same, right? And how about the top? Same. Now if I take this rotation, add it to this translation, and we're going to assume that the magnitude of these vectors is the same here. What do I end up getting? Well, here, what happens with these? They cancel, right? So here, I just consider some point P. What about the center of mass? What's it going to be doing? It's going to be moving, velocity v, and how about the top? It's going to be 2v, right? It's going to be twice the velocity of the center of mass. This is the velocity of the center of mass. And so this is the situation that we'll get when we add this pure rotation to a pure translation. We get this, what is pure rotation. Okay, so now, rather than think about rotation about the center of mass, we think about rotation about this point that is interacting with the ground, or that is touching the ground. Now there's a really neat picture in your book if you have time to look at it, but basically it's a picture in which they basically show that the spokes, as this is rolling along right here, down at the bottom, these aren't moving nearly as fast as these are, and so these become blurry, and the bottom ones are in color. The bottom ones are clear to see. Okay, so in pure rolling motion, if I assume that this distance here is r, or the distance between the center of mass and the point P is r, then I have that the velocity of the center of mass is simply just going to be if I look at the velocity of the center of mass, I can then find out, for example, rotation frequency. And so we just simply write this as the omega r, where omega is the rotational frequency of this particular system. Okay, so the rate at which this is spinning around. Okay, now this is for smooth rolling motion. Okay? And now the velocity at the top, how would we find the velocity at the top? Well, that's fairly straightforward. We can see that that's just twice the velocity of the center of mass, and so the velocity at the top is just going to be, well, you can see, for example, the radius is going to be twice as big, so omega 2r, and so if we get 2 omega r as the velocity at the top. when we think about this as rotation about this point. And it's an instantaneous rotation. Okay, so now let's consider the kinetic energy of the system. How am I going to consider the kinetic energy of this system? Yeah. Okay, so we have the kinetic energy of the rotation, we have the kinetic energy of the translation. Okay, good. So, but now let's consider how do I find the kinetic energy of something that's rotating? Okay, so we use 1/2 I omega squared, right, for the kinetic energy of something that's rotating. Now what we're going to consider is the rotation about this point. So let's look at this. So if I say the kinetic energy is 1/2 I, and I'm going to call it point P because we're talking about this, all that P here. So we're going to say that the moment of inertia about point P omega squared. Okay, now do I know what the moment of inertia of a spinning object is about a point out here? What do I know? I know how to find the moment of inertia of something about its center of mass, right? For example, if I have a wheel, that's very straightforward. In fact, a wheel is essentially just mr squared because the mass is all located about a radius away. So we just say that the moment of inertia about the center of mass is just mr squared. But I could also have a sphere, which is 2/5 mr squared. I could have a disk, which is mr squared over 2. So I do know the parallel axis theorem, right? Which means that I can rewrite this in terms of the center of mass plus the mass of the object times the radius squared. Since this is the radius that's going to be interacting with the ground, right, or that is going to be touching the ground, omega squared. So what we're interested in is what's happening as it rotates about this point, and that we've said that that's a distance r here, and this is the parallel axis theorem. So if I know the moment of inertia of the center of mass, then I simply need to just add mr squared, and that gives me the moment of inertia about the point r that is touching the ground. So if I look at this more carefully, I see something very important, which is that this is just 1/2 I center of mass omega squared plus 1/2 m r omega squared. And I wrote this because we said already that this is the velocity of the center of mass. And so I get 1/2 I center of mass omega squared plus 1/2 m v center of mass squared. So as was said earlier, what do we have? This is the kinetic energy for pure rotation, and this is kinetic energy for pure translation. That's pretty neat. And all we did was use the fact that we just used the parallel axis theorem, and that gave those two things to us. So this is kind of another way of showing that the sum, that this smooth rolling motion can be just considered the sum of pure rotation and pure translation. Questions? Everybody's happy? All right. So, now, if this is the, for smooth rolling motion, if the velocity of the center of mass is equal to omega r, then what would the acceleration be equal to? There's calm stillness about you today. Yes. Alpha r, right? So the A center of mass is just going to be equal to alpha r. So let's look at some things rolling down hills. Okay, now, suppose I have something rolling down a hill. So, for example, suppose I tilted this table up and I started rolling this bicycle wheel. Let's analyze the forces on this object. And I'm just going to erase this up here so it doesn't interact with our forces here. So what forces are going to be acting on this object? Gravity. Sorry? Normal force, and where is that going to be coming from? Okay, so we take that from the contact point, right? However, in the book, for example, they actually take it from the contact point and move it up to the center, but it's the normal force is the interaction of the surface with the thing that's rolling. Okay, what else do we have? Yes? Sorry?
Friction.
Friction. Now, if we didn't have friction, what would happen here? Would it roll?
No, it's straight down.
Right, it would just be pure translation, right? Try and make a wheel stand up without any rolling motion. That would be tricky, but it'll just go down without rolling, right? It'll just go right down. It'll be pure translation. The friction, though, is going to be acting in what direction? It's going to be going up, right? So we call this static friction because we're considering pure rolling motion. Static friction means that we don't have any slippage between the ground and the thing that's rolling. Anything else? No, there isn't. Okay? Good. So, how are we going to solve this problem? Should I do the moonwalk to help you guys liven things up? So I thought this was the coolest thing I'd ever seen when I was 12 and saw Michael Jackson do it for the first time. So I'm going to do it really quickly, and then we're going to go back to this so that your brains will be fully engaged. Okay, now, so let's break this up into axes. Okay, we're going to break this up into a XY coordinate system. some of the forces in X, we have the static friction, and what else do we have? Okay, so we have Fg sine theta, so we'll just say minus mg sine theta, and that's going to be equal to the mass times the acceleration center of mass. We just put center of mass to remember that we're considering this about the center of mass. Okay, do we know the force of static friction? We don't, right? The force of static friction, we often consider the maximum static friction. But now what we're going to consider is the fact that the static friction can be anything between 0 and the maximum static friction. And that's important to remember. So we don't actually know what this is. Do we know the acceleration of the center of mass? No. So we have two unknowns. Can you find two unknowns with one equation? No. So what do we have to do? Sorry? Okay, now the sum of the forces in y, that's a good point. So if we do the sum of the forces in y, we'll get that the normal force is equal to Fg cosine theta, right? But would that help us in solving either of these two things? No, it won't. What else can we use? I mean, it's a good try. Don't want to stifle any future creativity. Yes? Okay, so if we could put in alpha r here, but we still know what alpha is, right? Alpha is also unknown. That's a good try as well. Yes? Okay, so that's a good way of starting off. We'll do that in a minute, but not for this one, because that wouldn't actually tell us what the static frictional force is. What else can we use? How about the sum of the torques? Oh, good, we got it. Okay. Sum of the torques. So now if I look at the torque here, now what we're going to consider is we're going to still consider this rotation about the center of mass. Okay? So what we're going to do here is we're going to say that the R, okay, if I look at this just from the center of mass point of view, look at this static friction. Only the static friction is causing a rotation about the center of mass, right? The normal force is not causing any rotation of this object about the center of mass because it is in the same direction as the radius, right? So torque is R cross F, right? But if F and R are in the same direction, the torque is 0, right? So if I start pulling on my arm in the direction of my arm, it's not going to make my arm rotate, right? Only the thing that is only the components that are perpendicular to the radius are going to cause. Okay, now I could have something that isn't perpendicular to the radius, for example, but we would just find a component that is perpendicular to the radius. So what we want to find is all of the forces that are perpendicular to the radius. And neither gravity nor the normal force have any component that's perpendicular to the radius. Only the force of static friction, from the static friction. And so what we're going to say is that the radius, which is r, times this static friction, F of s, is equal to I times the center of mass times alpha. Now we have to do something, as was said earlier. I know alpha and A are related. In this particular case, so we have to be a little careful about signs that we choose here. alpha is related to A, we know through omega r. But we have to be careful because if we look at A is going down. In other words, A is going in the negative direction while alpha is going in the positive direction. Yes?
Why isn't the x component of your gravitational force calculated in your torque?
So why isn't mg sine theta?
Yes.
Okay, good question. So if I look at, where is mg sine theta acting? It's acting this way, right?
Yeah.
Now, which torque is, if we recall, let me just draw it up here. So the question is, why isn't mg sine theta exerting a torque on this wheel? And if I look at this wheel, mg sine theta is pointing this way. Which direction is the radius vector pointing? If I think about what's coming out in the direction of the radius, in the direction of mg sine theta, this is what I get. Okay, let me demonstrate that. Now I'm going to pretend I'm mg sine theta. Okay? That's funny. I've never pretended I'm mg sine theta before. Okay, but mg sine theta. Here's mg sine theta. Okay. Now let me lift this up a moment. So because there's a force on there. If I'm mg sine theta, I'm moving it like this. How much rotation did that cause? How much did it cause this wheel to rotate? It doesn't, right? If I put it down, what is the thing that's causing it to rotate? The friction. Okay? Great question. I gave an exam a little while ago to a graduate quantum mechanics class, and for the exam, someone dressed up like one of the mathematical equations we did in the class. So I'm not sure what an mg sine theta would look like, but maybe I'll dress up for that for Halloween. Maybe you can give me some good ideas. Okay. So, so if I look at this, basically all I get here is R times the static friction is equal to I center of mass alpha. Now, we know that this alpha is positive, but the A is in the negative x direction. So we just have to be a little careful. And so what we're going to rewrite this as is R, F of S is equal to I center of mass. And then we're going to say this is minus A center of mass all over R. Which means that if I can solve for this, the force of friction, I just divide by R. I see this is minus I center of mass. A center of mass over R quantity squared. R squared, that is. So now I have two equations and two unknowns. So I'm just going to, I see that I have F of S here, and I have F of S here. And I set those two equations equal to each other. Okay, so from here I see that F of S is equal to MA center of mass plus mg sine theta. And I see that F of S from the other equation is just equal to minus I center of mass, A center of mass over R squared. So I set these two equations equal to each other and then solve for A center of mass. So I see that I get minus I center of mass, A center of mass over R squared is equal to M A center of mass plus mg sine theta. I'm going to bring this over here, and so I get, and then I'm going to factor out A center of mass. A center of mass is equal to, I'm going to get a minus on, because when I bring this over, I get a minus MA center of mass, and I get a minus here. So I get I center of mass over R squared plus M is equal to mg sine theta. And so this implies that A center of mass is equal to minus mg sine theta all over m plus I center of mass all over R squared. Now, just to reconcile these things, if I pull an m out of both sides, right, if I out of the numerator and the denominator, then I just see I get minus g sine theta all over 1 plus I center of mass all over m R squared. So does the moment of inertia affect how things roll? What do you think? Does the moment of inertia affect how things roll? Well, let's look at this closely for a moment, right? If I look at this and I say this is g sine theta, 1 plus. Now let's substitute in, for example, for a hoop. Let's suppose I just had a big ring, right? If I had a big ring with all of the mass at a distance r, right? This is just empty. This is just a big ring around here. Is that going to have a higher center of mass than something where most of it is located at the middle? And so let's ask a question. So suppose this is just a big ring and it's mr squared, then what do I get? If this is mr squared for the center of mass, then this just becomes 1, right? And so a ring rolling down a ramp is going to just be whatever g sine theta is divided by 2. Now what if I have a solid disk? If I have a solid disk, then what does this become? 1/2, right? Because then it's mr squared over 2 divided by mr squared, and so I just get the 1/2. And so then it's only divided by, instead of divided by 2, it's divided by 3/2. So that one will roll faster, right? A solid disk will roll faster than a ring with all its mass at the edges, right? And if you get more and more mass closer to the center, right? If you imagine I had just something that was rigid but had no mass except for right at the center, it would just be 1, right? So let's do an example here. This isn't quite the same thing, but these two things weigh almost the same to within 25 grams. Except this one has almost all of its mass at the edges, right? There's a heavy metal bar at the edge and a light wooden center. And here there's all of the masses at the center, or close to the center, and with a light piece of wood on the outside. So we would expect that this one will go slower. Right? We're all happy with that. All right, so now, someone, can't remember who, some brave soul, discussed in terms of doing this in terms of kinetic and potential energy. So let's do this in terms of kinetic and potential energy. So suppose I have a ramp, and I have an object. Here we're going to assume pure rolling motion, smooth rolling motion. And what we're going to say is, what is the, we're looking for velocity? Yes, okay. So let me give you some parameters here. So we're going to say this angle is 30 degrees. We're going to say the mass of this object is 10 kilograms. And yeah, we're assuming that it's a sphere. And I'm just going to put maybe I'll put I center of mass of a sphere. Of a sphere is 2/5 mr squared. Okay, I center of mass for a sphere is 2/5 mr squared. The radius, we'll just assume, is r. And now, and the initial height is 1 meter. In other words, this height here is h, and by the time it gets down to the bottom, we want to know the final velocity. So we're going to start it from rest. We're going to let it roll. And by the time it gets to the bottom, we want to find out what its velocity is when it gets to the bottom, the velocity of the center of mass. So how would we do that? First of all, is there any energy lost into the contact of the rolling ball with the plane? In other words, is there sliding motion that would cause heat? Right? This causes heat, right? This doesn't. So, is there any energy lost there? No. So that means that we can use conservation of energy here, because all of the energy is transferred initially from kinetic energy, from potential energy to kinetic energy. So if I look at this conservation of energy, I have that K final plus U final is equal to K initial plus U initial. So what is K final? Yes. Okay, so we have U initial. Okay, so we have mgh. That's U initial, and we know that those two are going to be equal because U final, we're going to say is 0, and K initial is 0, right? So that means U initial has to be equal to K final. But how are we going to find K final? Okay, so we have 1/2 I center of mass omega squared plus, so this is the rotational kinetic energy. We also have translational kinetic energy, which is what? 1/2 mv center of mass squared. So we have the rotational kinetic energy and we have the translational kinetic energy is equal to the potential energy. Now, is the velocity of the center of mass and the rotation related? And the angular velocity? Is the angular velocity and the velocity of the center of mass related? It would look like we have two unknowns, but we really don't have two unknowns here, do we? We only have one unknown because we know for smooth rolling motion that omega can be written in terms of the velocity of the center of mass. So this is 1/2 I center of mass. Omega is equal to V over R, and then we square it. and I should say center of mass, plus 1/2 mv center of mass squared is equal to mgh. This looks like a capital M. Sorry. These are all the same numbers. So now we have, we need to know for a sphere. We said for a sphere that the moment of inertia for a sphere is 2/5 mr squared. And we get that this is 1/2 times 2/5 mr squared all over v over r quantity squared plus 1/2 mv center of mass squared is equal to mgh. Now we have an m in all of these equations. That means we can cancel them out, which is a pretty interesting result if you think about it, right? It doesn't depend on the mass, it depends on the geometry. It doesn't depend on how fast it's going at the bottom. It doesn't depend on how heavy it is. Just like when we did if you drop a feather or drop a ball in a vacuum, they give the same result. So now it becomes, this then becomes, I get a 2 that cancels here, so I get the 1/5. This r squared cancels with that r squared, and so I see that I get 1/5 times v center of mass squared plus 1/2 v center of mass squared is equal to gh. So I get a common denominator, which would just be 10. So I multiply these two, and I get a common denominator, so I get a 10. I'm going to bring a 2 up here, and I'm going to bring a 5 up here, so I get, this is 7/10 v center of mass squared is equal to gh. And that means v center of mass, just bringing this up, I get 10/7 on this side, multiply both sides by 10/7. And I see that velocity of the center of mass, take the square root, is 10/7 gh. And so, for example, this, if I say that this is, so if I just do this 10/7 times 10 meters per second squared times the height of 1 meter, then I get 10 times 10 is 100 divided by 7. That's about 15. Square root of 15 is a little less than 4. So I'm just going to say it's approximately equal to 4 meters per second. This just means approximately. So it's a little bit less than 4, but we're just going to assume it's 4 for the math in here. All right. Questions? This is doubly less than 4 because this is 7 times 15 is 105. So I actually just say 100 divided by 7 is approximately equal to 15, and then the square root of 50 is approximately equal to 4. So, but both of those approximations err on being too much. So it's, anyway, probably 3.78 or something like that. Now, how can we find well, let's go on to the next part. I want to make sure we have plenty of time for going through this stuff. Okay, so last time we talked about the yo-yo. This is a very fancy yo-yo. Right? Kind of a cool yo-yo. Except it would hurt your arm if you swung it too hard. Has anyone ever seen Devin Supertramp? Okay, he has some cool videos, but one of them is he has one of the world champion yo-yo guys. You should watch it. Okay, so Anyway, let's see if we can predict the motion of this yo-yo. Essentially, this is a fancy yo-yo that's heavy. Actually, I'm pretty good with the yo-yo. I can walk the dog. I can kick the dog. No, that's about all I can do. Let it go down there, kick the dog, say bad things to the dog. But that's okay. So if we look at this yo-yo, this is basically a simpler version of something that we just did. Now, what we have is a string coming down. We have a tension, and we have the force due to gravity. Right? So if I were to look at that, I once again have two equations and two unknowns. Right? I have a tension. So if I look at some of the forces in the y direction, I get T minus force due to gravity is equal to A center of mass. Oops, sorry. MA center of mass. And then I also have a torque equation. Right? The torque, in this particular case, alpha is going one way, and the A center of mass is going another way. So what I'm going to say is that, but we have to be a little careful now, since this radius here, at where this is, this axis of rotation, if I were to look at this, right, the center of mass of here and this little tiny radius here is different than this radius going out to here. Right? The tension is causing a torque about this very, very small radius here. So what I'm going to say is that if I have the torque, so let's estimate this, 5 millimeters. So I'm going to say that the radius here times the torque, the radius times the tension is equal to I center of mass A alpha. Now one thing that's different here than different before, if I solve for tension in this equation, so we have two equations and two unknowns. This one comes from the sum of the forces, this one comes from the sum of the torques. There's something very, very different, though, in this than the one that I just previously did, which is that the sum of the forces, I get T is equal to MA center of mass minus or plus FG, or I'll just put MG. And for the sum of the torques, I see that I get a T. I can solve for T. T is equal to I center of mass divided by, and now what I'm going to say is that this radius here, I'm going to call R1. So I'm going to call that R1, and this radius here, I'm going to call R2. Is the center of mass going to be given by, so let's just assume that this is a disk. It's actually not a uniform disk because most of its mass is towards the end, and it's thinner in the middle. We'll just assume it's a disk for the purposes of this class. So the I center of mass here, the I center of mass is going to be given by what for a disk? Okay, so this is going to be MR, is it R1 or R2? If I have a disk here, is the moment of inertia going to be governed by this radius or by this radius? By radius 2 or by radius 1? By radius 2, right? Since the disk has a radius R2. Okay, so I'm going to write this out. And then I'm going to say this alpha okay, so if I divided by this radius 1 here, right? Okay, so now if I look at this, the center of mass, the acceleration of the center of mass is going to be given by what? So how would I relate alpha to the center of mass here? Yes?
I have a question.
Yes?
What is the difference between R1 and R2?
Okay, a good question. So let me draw this. It's hard to see. It's probably too hard to see back there. So here's my yo-yo. I have a tension coming up here like this, right? And I have a mass, mg, coming down like this. This distance is the distance over which the tension acts relative to the center of mass. Okay, so this is what we're calling R1, and the distance or the size of the disk is R2. Is that clear? That's really important to understand. Right, so we're exerting a tension on a much smaller radius than the actual radius of the disk. Okay, the next thing, alpha. How am I going to find alpha? I want to write alpha in terms of A as center of mass. How am I going to do that? Okay, so I'm going to take the center of mass. So this is equal to I, center of mass. And then I'm going to say that this is A, and it's minus, right? Since now this is what we're calling negative, but this is a positive rotation. So this is a minus A, center of mass, divided by R1 or R2. In this particular case, it's R1. Because if we think about it, what we're doing is we're rotating about this. This is the axis, if you can think about it for a moment. What we're doing is we're causing a rotation to occur about this point instantaneously. Right? So that string is causing that string is being held at this point, and this whole system is rotating about this point. Right? It's not being rotated about a point at the edge of the disk. It's being rotated around a point that is this distance right here. All right? Everyone sees that? Right? With a wheel moving on the ground, we always say we rotate at the radius or the size of the wheel. But here, what we're doing is we're causing a rotation about the point associated with the string touching this. Right? So if you want to think about at any one individual time, that tension is lifting up on the at that point, and it's rotating about that point. It's not rotating about a point if I were to have a string coming out here. All right. So if I do these equations out, I can see that the t is therefore equal to minus, and then I'm going to do the m, and we're going to use this r2 squared, mr2 squared all over 2, multiplied by minus a center of mass all over r1. Oops. Sorry, this should be r1 squared because I have an r1 here, and then I'm multiplying by, so I should have an r1. There should be an r1 here, and there's also an r1 that's brought in as I convert alpha to center of mass divided by r1. So I have an r1 squared here. Okay? And so we get that this is minus m r2 squared all over 2 divided by r1 squared, a center of mass. Now this is a very nice result, because what you can see, well, let's finish solving this out, and then hopefully that will become clearer. Then we see that this gives us m, a center of mass. So I'm just setting this equation right here equal to this equation, m, a center of mass plus mg is equal to minus m r2 squared all over 2 r1 squared, a center of mass. And so I see that if I just bring this over to this side, or sorry, bring this over to this side, I see that this gives me, and I'll cancel the m's. And so we see that we get, this is g is equal to minus a center of mass. We're going to get an r2 squared all over 2 r1 squared plus 1. Now, if I take and solve here for a, then a center of mass is equal to minus g all over 1 plus r2 squared all over 2r r1 squared. If r2 squared is much, much larger than r1 squared, then we can ignore the 1, and we can get a good approximation here that this is equal to minus g, and we're going to get a 2g r1 squared all over, and let me put approximate, r2 squared. So now we can see that the center of mass, the acceleration of the center of mass becomes a this acceleration can be dramatically slowed by having a large r2 relative to r1. So that's the case that we have in this particular situation. In this particular situation, we have a very small radius, say 5 millimeters, divided by, say, 5 centimeters, something along that line. And so we're getting, say, an order of magnitude larger radius, which means that it will be slowed. Essentially here, its acceleration will be slowed by a factor of 100, approximately. Okay, and then this 2 factor out in front. But I just want to point out that this dramatically slowed down how fast this mass accelerated downward. Time to soak it in. So I want to touch briefly on torque and angular momentum. We already we said earlier that torque is equal to R cross F. And let me just remind you what that means. If I have a radius vector here, R, and I have a force vector here, F, then I take R, I take my fingers. So if I were just take this here and I say, what is the torque, the direction of the torque? I take R, I cross my fingers into F, and that's the direction of the torque. So in this case, the torque's here. What if the force were down like this? Which direction would it be? So now I change the force to being downward. Which direction is the... It's into the board, right? Now, what if I said, I know that the torque is out of the board? Which direction is the force acting? How would you do that with the right-hand rule? So let's say the torque is out of the board. Okay, good. What you can do is, you know that the thumb is going to point in the direction of the torque, and your fingers point in the direction of R. So that means you just need to go like this, and then whichever way your hand wraps naturally is the direction of the force. Okay? Or force is acting somewhere along this direction, right? So you put R in that direction, you put your fingers in the direction of torque, and then you would be able to know in which direction the perpendicular component to R is acting. Okay? So you should be able to do that fairly straightforwardly with the right-hand rule. Now, and the magnitude of the torque, we just write as this. We say this is the magnitude of the torque, R cross F, which is equal to R F sine of phi, where if this is the angle F, this is the angle phi. It's the angle relative to F. It's the angle of the radius vector relative to the force vector. So that's how you find the magnitude. Now, angular momenta. Angular momentum becomes also a very angular momentum is defined as if I have a particle of mass m and moving with the velocity v, and I want to find its angular momentum about an origin here, then the angular momentum, which we write as L, it's a vector, is r crossed with p, which is just equal to r cross mv. Okay, so I take r, I cross my fingers into the direction of v, and that's the direction of my angular momentum, which is coming out of the board. And you can see very easily here that, for example, if I have a situation where r isn't changing, and I take dl dt, then I get that this is r crossed with f. ma, which is r cross f. And so you can see we end up getting something that looks like torque again. So the time rate of change of the angular momentum is the torque. But we'll talk about that more next time. So let's do a quick example here of angular momentum. And next time we will spend some quality time doing bicycle wheels. This was actually made a mistake in bringing that up prematurely this time, but it was useful for demonstrations. And this chair, and we'll talk about conservation of angular momentum. And it's quite an interesting thing. How many of you like to race motorbikes? Motorbikes? BMX? Or actually not BMX, like farmer jump. Okay, have you ever seen those jumps where they go up into the air really, really high? high, and then they're able to aim their bike so it's going straight down the ramp and hits it perfectly. You ever wondered how that's possible? Right? It's not like they take off and then suddenly they just have the nice trajectory to just go like that, right? How do they do that? Does anyone know? No one races motorbikes? There's got to be one race along here. You? I think you race motorbikes. Okay, well, we'll talk about that next time. But anyway, so angular momentum. So this is just a quick example in the book that they give. For example, if I have two particles going like this, one's moving this way, one's moving this way, how would I find, let's just do it qualitatively, how would I find the angular momentum? Well, if this is moving with velocity v2, and this is moving with velocity v1, how would I find the angular momentum about this point of these two particles? Well, the first one, if I take the mass 1, or I take this radius vector 1, wait, sorry, I didn't put it. Which direction is the angular momentum going to be pointing for this particle right here? So I have R crossed with V, it's coming out of the board. How about this one? Into the board, right? So I take R crossed with V, and that goes into the board. Now the same equation that the same type of thing that we did before, if I simply want to find L total, that's just simply L1 plus L2. And in this particular case, if I want to find its magnitude, all I'm going to do in this case is I'm simply just going to add L1 plus L2, since they are both in the same line, right? L1 is coming out and L2 is going in, and so we can just add them linearly. We don't have to add components. Okay? So L1, I would just take the magnitude of R1 crossed with MV1 plus the magnitude of R2 crossed with MV2, M1 V1, M2 V2, which is just going to be equal to R, and I'm only doing this because this is, right, L1 is going this way and L2 is going this way. They're both on the same line, so I can just literally add their magnitudes, right? If L1 was that way and L2 is this way, I'd have to break them up into components on X, component of Y, and components of Z. But here I'm just going to write it like this. And so I have R1, so I'm going to take R1, M1, V1, sine of the angle between them, plus R2, M2, V2, sine of the angle between them. Now that gives me the total angular momentum, and phi1 here, right, is just the angle between these. That's phi1. But since it's going back like this, and then this angle between them here, we just need to be careful how we write these angles, and that will show that one's being positive and one is negative in terms of an axis that comes in and out of the board. Okay, I know we are out of time, so thank you. Hope you have a great day.